In the last segment, we talked about one specific contrast, the difference between beta 1 and beta 2. Now we're talking about contrasts in general. So we have a linear function of the betas here. A is a vector and with the same number of entries as beta, of course, so p plus 1. And so the new statistic that we want to make inference about is then the product A transpose beta. And the test is just as before. Now, what we need to figure out, though, is how do we compute theta hat and how do we compute the standard error of theta hat. We had previously shown that beta is distributed as multivariate normal, multivariate because it's not a scalar, it's a vector, as follows. And the linear combination of a normal distribution is also normally distributed, and we have a linear combination here. So given that we know it must be normally distributed, we just need to find, well, just in quotation marks, the expectation and the variance. Using linear algebra, the expectation is just A transpose beta. And for the variance, we have to take the transpose out and for the A transpose out in front, and we have an A in the back. And the variance of beta, we already know that's in here. Yeah. So we have the variance of A transpose beta. The A goes out in front and in the back. And here in the middle, we have the variance of beta. Once we have the variance, we get the standard error as usual by taking the square root. And in this particular case, we have a sigma squared, so we can get that out, 1 sigma. So let's look at this special case, a single parameter, just to fix ideas and make sure that this makes sense to us. So if I just want to make inference about beta 1 or beta 2 or beta whatever, at the ith position, then the vector is 0, except it has an indicator 1 at the ith position. And we're using this vector definition, then AT times beta is just beta I. So we know what the variance of beta I is. It's that square root element of the variance covariance matrix at the ith position. And let's see whether this collapses into that same answer. So variance of theta, we have said, is this expression. And here in the middle, we have the variance of beta. Now, given that A is just a bunch of zeros with a 1 at the ith position, this pre-multiplying and post-multiplying of A, what it does is it just picks out that ith position in the diagonal of the variance matrix. So we indeed get the variance of beta I. Okay. Let's do the same thing again for a different special case. We are now looking at the difference of two betas and trying to see whether we get the same formula based on the general formula for the specific case of a difference. So in this case, we have in the ith position, we have a 1, and in the jth position, a -1. So before we had beta 2 minus beta 1 minus beta 2, I think. And so if we do that, then A transpose times beta just results into beta I minus beta j. So that's what we wanted. So on the next slide, we're looking into the variance, right? So we know it's a linear combination of normal, so it's normal. So we need to figure out the expectation and the variance expectation we have here. So the variance, we have AT transposed in front, we have a 1 and a 1 minus 1, and here in the back. And then we have that variance comatrix. And what these four elements do here, what the one and the minus one do here, they operate on these four uh, elements in the matrix. We have the variance here and the covariance. And we remember that this is a symmetric matrix, so the value Cij is actually equals the value Cji. So if we pre-multiply the transpose, we get this vector. We post-multiply um, the A there, then we get this difference, and then we have the two variants add up. There's a minus minus here, the two variances, and then given that Cij equals Cji is, we have minus twice the covariance. And that's exactly the formula we had before. Variance plus variance minus twice the covariance. Yeah. And I'm repeating it here, variance minus twice the covariance. Okay, so that's the same thing. Here is a question for you. What is the variance of this linear combination? Variance of beta 1 minus 2 beta 2 plus 3 beta 3. I have 5 different answers. One of them is right, and I'll leave you to answer this.